All right, so let's think about what that process might look like mathematically. So maybe we'll say the arc length L, we're approximating this, okay, this is just an estimation, so we'll use a little squiggle. We're going to use the distance formula, which was x1 minus x2 squared plus y1 minus y2 squared. We're going to use that as many times as possible because the more individual lengths we have, the more accurate we are. And then we want to add all those up. Are you guys familiar with kind of the mathematical or Greek symbol we use that means adding everything up? I probably showed it to you once or twice. We didn't formally use it. Yeah. Okay, we're going to use it a lot more this year, yeah. Sigma, do you know what it looks like? It's a big E, yeah, or a weird looking big E, something like that. Sigma, okay? So the way I'm writing this is very informal. Okay, we're going to eventually discuss how we will have to write something underneath and on top of that E. Okay, you don't have to put in those circles there, but there are other pieces to that E that should be there, but I'm not going to write because we're not there just yet. We're eventually going to get there this year, but not right now. Okay, so what this is informally telling us is we're going to take all of those individual distances that we can calculate and we're going to add them together. That E just means to add together. So what we're going to do is we're going to take our understanding of this and turn it into calculus using calculus symbols. Okay, so let's think about, in terms of calculus, how might we be able to represent x1 minus x2? Yeah, dx, okay? It's a change in x values. If you have one x value and you subtract another, you're finding the difference between them. So you could use dx. Remember how dy over dx represents a derivative? Change in y over change in x. We also have the notation delta y over delta x. Maybe from like a science class you've seen that delta triangle symbol before. So if you want to use dx, you can. If you want to use delta x, you can. Do we have a preference as to which one you want to use? We're used to the dy's. Okay, if you want to use the deltas, that's okay too. So we'll say this is dx squared, which then must mean if we do y1 minus y2, that's a change in y, aka dy squared. This comes from slope, right? If we do y2 minus y1 over x2 minus x1, slope is the same thing as derivative, which is the same thing as change in y over change in x. It doesn't matter if you do y2 minus y1 or y1 minus y2, it's still representing a distance in the, or a difference in the y's. Okay, are we okay with that change in notation? All right, take a look at what I'm going to do next. I want to see if you guys understand where this is coming from. Why was I able to go from that second line to the third one? What do you see? Yeah. Exactly. If I were to actually square dy and square dx, this would be dy squared over dx squared. But notice how this dx squared would cancel out with this dx squared, and we would just be left with the dy squared we had previously, right? So these two statements are exactly the same, they just look different. I'm putting in this dx squared portion to help us rewrite it a little bit more. Okay, but do we see how that's mathematically appropriate? They're still equal to each other. They're still the same thing. Okay, so let's see. We have a dx squared as our first term, and now we have another dx squared in the second term. Maybe we can factor a dx squared from both terms. It's not coming out of the square root. We're just factoring it out of the two terms individually. So it's still under the square root. So if we pull that term out, we're left with 1 plus dy over dx squared. So far, so good? Okay. Now let's think about if you're multiplying two things together inside of a square root. Notice how we have the dx squared times that leftover factor squared. You can take the square roots of each individual term. So how can we rewrite the square root of dx squared? Yeah. Just dx. Yep. Now, unfortunately, the second term is comprised of a sum. Okay, you're adding two things together. So you cannot break apart that into the square root of 1 and then the square root of dy over dx. Whenever you're adding or subtracting inside of a square root, things go a little crazy. You cannot break up those individual pieces. So this section is just going to stay that 1 plus dy over dx squared under the square root. Are we doing okay? It's not over our heads yet, is it? No. I don't expect you to remember this. I just want to show you where the formula at the bottom of the page is coming from. Okay, why we're able to use this. Okay? All right, so let's think about some calculus notation. Instead of that E sigma, what have we introduced in calculus that kind of represents the same idea? Adding things up, yeah. An integral, right? We use that integral symbol in terms of the rectangles, those Riemann sums. Okay, so instead of a sigma, we can use an integral. Typically, the dx in the integral goes on the end, right? But if you're multiplying two things together, order really doesn't matter. So if we want to move that dx to the end, we can, which means the square root portion will be written first. And instead of dy over dx, do we have a similar calculus notation to represent a derivative? Yeah. F prime, y prime, something like that. Maybe we'll use f prime. So what we did is we developed the generic formula, I guess, for finding the arc length of any curve. You see that at the bottom of the page, how it matches? Now the A and the B are just representing your bounds again, like the beginning and ending point, okay? But we developed that calculus formula. So from now on, I don't expect you to remember those steps, but we will have to know that arc length formula, okay, the setup at least. So we're going to use that today in some examples to help us calculate the length of curves, not necessarily straight lines anymore. Okay, so let's go ahead and take a look at the first one on the next page. Let's say we are walking along the path natural log of secant from 0 to pi over 4. At the end of our stroll, how far have we traveled? All right, we'll give an approximate answer. Exact means you do it by hand. We'll save some time with our calculator. So we got to set up our little formula here. Notice how we're walking along a curve. It's not a straight line. So if we're walking along a curve, we have to figure out the length of that curve. We need the integral from a to b of the square root of 1 plus the derivative of the curve squared, and then dx. So we're going to fill in those different portions of the arc length integral formula to help us answer this question. So can we identify the bounds? Where we start, where we end? Yeah. 0 to pi over 4. And next we need the derivative of the curve squared. So let's go ahead and try to figure out the derivative. So the curve is the natural log of secant. How might you want to find the derivative? Do you remember our natural log derivatives or trig derivative shortcuts? These are kind of the trickier ones. Yeah?
Is it 1 over secant x times cosecant x?
Okay, so the natural log is 1 over the inside, in this case secant, okay? And we do have a chain. We have to multiply then by the derivative of the inside. Do you remember the derivative of secant? It's not just secant.
I said cosecant.
Oh, I'm sorry, it's not cosecant either.
Oh, it's cosecant.
Other one.
Cosecant.
You gotta use the other reciprocals and you got it. It's not cosecant, cotangent.
I had this memorized last year.
I know. It's secant tangent. So we have 1 over secant times tangent. Hopefully we realize the secants are going to cancel, and we're just left with tangent. Okay, so we need tangent squared. The derivative of the curve squared.
Excuse the interruption. Some of the students who were taking the aspects are returning to class. So if you're not in your room, please get there. Thank you.
All right. So from there, we'll let the calculator do the work. You could do this by hand. You would have to realize that 1 plus tangent squared is a trig identity. Like, you know how sine squared plus cosine squared is 1. Okay. You'd have to realize that's an identity to simplify it a little bit further. But we'll go ahead and let the calculator do the work. Make sure you're in radian mode because we're dealing with trig. .881 units. Do we know the units? Miles. Okay. We doing okay? All right. It all boils down. You just got to know the formula and then how to plug things in. Okay. Nothing too tricky. I mean, it could get tricky when finding the derivative, but we're pros at that because we did it last year. Maybe. All right, let's try the next one. Find the exact length of the curve from 0 to 1. So let's maybe find the derivative first. See, we got a power rule. If we bring down the 3 halves, that'll change the coefficient to 2 square roots of 2. The 3's would cancel, and then the 4 divided by 2 would change to a 2. If we subtract 1 from the power, we're left with 1/2. And then the derivative of -1 is just 0. That looks a little weird. Can we rewrite that anyway? 2 square roots of 2, x to the 1/2. What does the power of 1/2 mean? Square root. So we essentially have square root of 2 times the square root of x, which we could rewrite as the square root of 2x. You can multiply those quantities together. Alright, so there's our derivative. So in terms of our arc length, we need the integral from 0 to 1 to give us the bounds, which is nice. And then square root 1 plus the derivative squared dx. Now this one we're actually going to do by hand. Okay, I think we'll be able to do this one. So can we simplify the inside of that integral a little bit further? If we actually square 2 square roots of 2x, yeah, 8x, perfect. Okay, so now we got to find an antiderivative. We're going to work backwards. So think of your integral techniques, okay, antiderivative techniques. How might you want to go backwards from a square root of 1 plus 8x? Yeah? Okay. So 1 plus 8x to the 1/2 certainly can do that. Maybe that helps something or some technique to pop out a little bit more to you guys. What are we thinking, or what do you want to try? Yeah. Add 1 to the power. Oh, so you're going to do that reverse power rule. Right. You could do that, but notice how we have multiple things on the inside? Okay. Where did you do something else in addition to that, or is that all you did? So did you have, let's see, add 1. So that would be 2/3 times 1 plus 8x to the 3/2. Did you leave it like that? Okay, there's a little bit more to it. You're on the right track. Yeah, Caitlin?
U substitution.
We're going to do u sub. Okay, you have an inside piece. So then derivative du over dx would equal 8. So we're going to have to rewrite this integral. Let's see, we would have u to the 1/2, and then solving for dx, we would have du over 8. Right? You got to use the derivative equation to help you solve for dx. So now, Cameron, we're going to use your rule. Okay, add 1 to the power, which would be 3/2. Your coefficient is 1/8. So we're going to multiply 1/8 by the reciprocal of that new power, which would be 2/3. 2/3 times 1/8. Oh, see, we divide it by the new coefficient. So we got to add 1, which would be 3/2, and then divide that by the coefficient. So 1/8 divided by 3/2. 2/24 or 1/12. Okay, so we're left with 1/12 as the coefficient. And then if we added 1 to the power, we would have u to the 3/2. Do we need the plus c? No, because we know the bounds. Okay, so we need to evaluate 1/12, and then instead of u, we can go ahead and substitute in what we said u was, that 1 plus 8x. And we got to evaluate from 1 to 0. Alright, so let's do a little figuring here. If we were to plug in 1, okay, top bound minus bottom bound, we would have 1 plus 8, which is 9. So then we got to figure out 9 to the 3/2 power. You can either cube 9 first and then take the square root of that number, or you can take the square root of 9 first and then cube that value, which either one's easier. Which one do you want to try? Do you want to cube 9 or square root 9? Square rooted. Okay, so square root of 9 is 3. 3 cubed is 27. So then 27 times the 1/12 would just be 27/12. And then we have to subtract what we get when we plug in 0. So we'll just have 1 to the 3 halves, which is 1, times a 12th is just a 12th. So 27/12 minus 1/12 is 26/12. I have arrows going every which direction here. 26/12, which can simplify to 13/6. If you wanted to double check on your calculator, just make sure you did it correctly, you could. Okay, you could simply type in your integral and hopefully you get 13/6. Okay, so some of these we're going to use a calculator, some of them we should be able to do by hand. Okay? Alright. Do you know what? We're going to save these next few for tomorrow because they're a little bit more involved. We have to pay close attention to something. So, in the remaining time, if you want to try some of your homework ones, you could probably do that. Is that okay?